Hi, I'm Olivia, everyone's favorite math teacher, and we're finally going to start talking about calculus, or at least the thing that led to calculus. So here it is. This is the operation that allows calculus to work, okay? So let f of x be defined on an open interval containing a with the exception of a itself. Now, what that first part means is just that we have some function that's on an open interval, so as opposed to last time where we were on a closed interval working with secants. And specifically, we have some value we care about that the function does not have to be defined at. So basically, this is like when we were looking at the velocity issue, and when we were trying to find the velocity at 5, we had the problem of when we tried to look exactly at 5, we were dividing by 0. So our rate of change was undefined there because we divided by 0. The limit says, well, that's fine, we can be undefined there, as long as we meet a specific criteria. And that criteria is that the function itself, okay, as x approaches a value we care about, and in this case, the example we used was 5. So this would have been as x approached 5, okay, the f of x had to approach a specific fixed value. So for us, it was 49, okay? So if our f of x is equal, or rather, the limit of f of x is equal to L as x approaches but is not equal to a, if all values of f of x are approaching L as x gets sufficiently close to a. Basically, what this means is, as we continued to get x closer and closer and closer to 5, f of x continued to get closer and closer and closer to 49. And so that value that f of x was approaching, x was never going to equal 5 because that would make our function undefined. But because f of x continued to approach 49, we can say that eventually we would get sufficiently close to a. We demonstrated that, well, we could do this forever, and we would get sufficiently close to a that basically f of x is equal to 49. Okay? A way to think about this is, think about two little kids. And one little kid is going, hey, I'm not touching you. 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 Until the other little kid snaps and goes, stop it. Yes, you were. Right? That's basically what's happening here. You keep getting closer and closer and closer and closer and closer until the function says, hey, we're good. This is our value. Okay? Now, there are some rules about this and how this works. And there's some pretty cool ways that we apply this, and we're going to look at this. And if this seems like a, well, okay, yeah, that works, then yeah, it is. It's a pretty straightforward idea. But it has one very, very powerful application because it allows us to get around a problem we have with rational functions. And that comes back to that problem we had with the velocity issue. We'll look at that in a moment. Okay, so this is our problem from the last video. Uh, we have our function for the falling object here, okay? And we're trying to find the velocity at 5 seconds. And if you recall, this was an issue of trying to find the tangent at a point. And the problem is that if we plug 5 seconds into our function, it's undefined, meaning that we can't find the tangent at this point. We cannot find the slope of the line at that point because we only have the one point. how do we do it? And we used the approximation method. And what the limit does is it basically formalizes that approximation method and turns it from an approximation into an equal. So now instead of saying, well, it's approximately this answer, we go, no, it is exactly that answer. You can use this as a solid set answer because it's getting there. As long as x can get sufficiently close to a, meaning that f of x has to constantly be approaching a value, and that's important, and that x can get consistently sufficiently close to a. Okay? Those are both there. But then the third part is that x will never equal a. And the reason that's important is because the problem with the tangent is that we were always dividing by 0, which means even though we could divide our factor out, we're still dividing by 0 because we would plug the 5 in here, we're dividing by 0. We can't just get rid of it. So if we take the function and we plug in 5, we go to 5, we're undefined. But if we sneak up on it, no, we're good because we didn't actually get there. We just got real close. We just kind of slid over to it, stood real up close next to it, and we were like, take the picture while I'm here. It's kind of like one of those terrible YouTubers who stands next to the car that isn't theirs, takes the picture and acts like they own it. That's basically what the limit's doing. And that's also kind of what that definition is doing, because that definition, unfortunately, does not say how close x has to be to a, which can lead to some problems when you are attempting to approximate, as we will see in just a moment. Here we have a function that's similar to one we've been looking at, but quite a bit different because it's not a velocity and it's not a related rate in the same way. So we're not looking for a tangent in quite the same way, but we're still looking for an undefined point. And if we go look at s of -2, you'll see that it is undefined at -2. And we know that because if we look at the function and you attempt to put -2 in there, we get -2 squared is 4, 4 minus 4 is 0. We're dividing by 0, we can't do that. However, when we take the limit and we say, well, we're not actually going to get -2, suddenly we can factor, divide out the x plus 2's, and we get 1 over 2 minus 2. And so when we put -2 in there, we get 1 over -4, which is -0.25, which, as you can see from our table, is what f of x is approaching as x approaches -2. So that would be our limit according to our limit definition. Now, one thing that I wanted to point out here is that we come at that limit from the left and the right. Basically, we come at it from the positive x direction, where x is bigger than the a value, and we come at it from the negative x direction, where x is smaller than the a value. And we actually define the left and right limits using those conventions. So we would say that the limit as x approaches a from the right, using a positive in the exponent position, of f of x is equal to L if f of x approaches L as x approaches a and x is always greater than a. So in this situation, x must be greater than a. And then the limit from the left is similar. We would say that the limit as x approaches a with a negative in the exponent position of f of x is equal to L. And again, if f of x approaches L, as x approaches a and x is less than a. And remember, this is a strictly greater than a and a strictly less than a because x can never equal a under the limit operation. So using the left and right limit, we would actually have another way to define the limit, and we would say that the limit as x approaches a of f of x is equal to L if and only if the limit as x approaches a from the right of f of x is equal to L, and the limit as x approaches a from the left of f of x is also equal to that same L. So what's interesting here is this actually also allows us to take a limit from the left or the right where maybe the limit only exists from the left or the limit only exists from the right. Let me show you an example of what that would look like. Here we have a piecewise function, and as you can see, if we come along this function, up here it exists at 4, 6. It does not exist down here at 4. So down here, it's undefined, but up here, it's defined. Let's take the limit of this function at 3 places. Let's take the limit as x approaches -4, the limit as x approaches 4, and we'll take the limit as x approaches 8. Now, this is a nice smooth limit, so we can go ahead and do this without the table. We'll just actually do it by examining the graph itself. If we come along our graph, coming from this direction, we come at -4, and we're getting increasing, and we get to -4, and we see that we're at 4. Now we come at it from the other direction, and we're constantly decreasing, and we're approaching, and we get to 4. So we can say that the limit as x approaches -4 of f of x is equal to 4, which you can clearly see on the graph. Now, if we were to look at the limit as x approaches 4, coming at it from the left, well, it looks like it would be 4. But coming at it from the right, it looks like we're approaching 0. So because the limit from the left is 4, but the limit from the right is 0, we would say the limit as x approaches 4 does not exist. I'm just going to write that as D in E. It does not exist. And then if we look at 8 instead, well, that's just like the previous one. As we approach from 4, or as we approach from the left, we come to 2. And as we approach from the right, we come to 2. So we would say that the limit as x approaches 8 of f of x is 2. However, if we said the limit as x approaches 4 from the left of f of x, we only care about x coming in from this direction. So we would say that that would be equal to 6. And then from the right, we would say that the limit as x approaches 4 from the right of f of x is equal to 0. Now again, it doesn't matter that it's undefined at 4, and it doesn't matter that it is defined at 4 up here, because we say it doesn't necessarily have to be defined there, and that we are approaching. And that's how we use the limits here. Now, I did say that we were going to look at graphs where it's a little bit problematic. So let's look at that example, and then we'll look at one last thing. So let's take a look at this graph. Clearly, this graph is doing something a little bit funky, and I'm going to tell you right now, the limit for this graph doesn't exist. But if you were to come into here and do something like simply put in, say, -0.3 and 0.3, you have a table here where you could conclude that the graph is approaching 0. And without the image of the graph, with just the table, it would be hard to argue with that because of the word sufficient doesn't say how close you have to be. And I mean, you're within zero point 0.3 and you're approaching the same value from both sides, so wouldn't that be sufficient? You look like you're approaching 0. And if you put a value in that is closer than that, it seems like it would work. Like, for example, let's go 2/3. If we say f of 2/3, we get a value of 0. So it seems like it's completely reasonable. But when you look at the graph, you see that this graph, as it approaches 0, oscillates between the values 1 and -1, meaning that f of x doesn't approach a single L. It oscillates between those values. So the limit doesn't exist because it doesn't fit our rule. So we can look at some other graphs. Here, the limit doesn't exist because clearly these values are not approaching the same L. Even coming at 0 from the right, they're not approaching a single value. They're going off forever. But this brings us to another kind of limit that has a little bit of a contentious notation. So we've been talking about finite limits, but there is another kind of limit called an infinite limit. And these are limits that indicate an asymptote. And the notation for these is where the kind of contentious issue comes in, because these limits are sometimes written in this way. Now, the reason that I say it's contentious is because this is saying that the limit is equal to infinity. However, infinity is not a value, so it's not really equal to infinity. What this actually means is that the graph is constantly increasing, indicating that as x approaches the value we're talking about, in this case 0, so I could replace 0 plus, so I could say that, x is approaching 0 plus and x is approaching 0 minus, that there is a vertical asymptote there. So there's a vertical asymptote as we approach from the right, there's a vertical asymptote as we approach from the left. And then if you were to look at, say, something like this graph, because both of these are approaching the same asymptote, you would say the limit as x approaches 0 from the left of f of x is constantly increasing, and the limit as x approaches 0 from the right is constantly increasing. Therefore, in this situation, just like with a finite limit, you could say that the limit as x approaches 0 of f of x is constantly increasing. So infinite limits work in a similar way notationally to finite limits, but you do have to be careful with this concept of equals infinity. So that was the conceptual definition of limits. I hope you found it helpful. And if you have any questions, remember you can always drop down into the comments or join us on Discord. In the next video, we're going to look at the laws for limits as they apply to functions, and we're going to learn about the squeeze theorem, a very important theorem that you use throughout calculus.